Hello, my name is Frances Staples and I'm a PhD student at the Mullard Space Science Laboratory at UCL. Today I'm going to be discussing some work where we use phase-space density measurements to examine dropout events caused by magnetopause shadowing. Dropout events are where we lose flux in the outer radiation belt by orders of magnitude, usually prior to a geomagnetic storm, and they are thought to occur due to magnetopause shadowing. Magnetopause shadowing might occur where there's a compression of the magnetopause such that it intersects electron drift paths, and this is called direct magnetopause shadowing. If ULF wave activity in the magnetosphere is high, then we can get indirect magnetopause shadowing if electrons diffuse outwards towards the magnetopause boundary and are subsequently lost. Turner et al. In 2012 characterized how phase-space density would look as a function of L star through a dropout induced by direct magnetopause shadowing, and this is shown in figure 2. Such a dropout is extremely difficult to measure with phase-space density in this way because it occurs on such short timescales, which are less than the Van Allen probe orbit. In order to resolve these changes, we use a multi-mission data set of phase-space density, including Van Allen probes, Themis, MMS, GOES, and GPS data. We investigated an event in 2017, which had a complex set of interacting CMEs driving a geomagnetic storm. An overview of this event is shown in figure 3. The top panel of figure 3 shows how phase-space density changes through this storm and demonstrates the resolution which we are able to obtain with such a multi-mission data set. We selected 4 one-hour time periods where we created phase-space density profiles as a function of L star, and each time period corresponded to a different stage of magnetopause shadowing shown by Turner et al. In 2012. We found during the first high pressure phase, where we had measurements of the magnetopause within geostationary orbit, that the last closed drift shell was compressed within the hour down to an L star of 3.7. During the hour, the phase-space density profile evolved as particles were lost at high L star due to direct magnetopause shadowing. When the pressure relaxes in panel C, we find that there is now a peaked distribution in phase-space density. And above an L star of 3.8, there is a negative gradient in the phase-space density profile. Panel D that we show differs significantly from the panel D in Turner et al. Of 2012. First of all, we have a growing peak in phase-space density at an L star of 3.8, and this will be due to localized acceleration processes, which indicates we are in the net acceleration for part of the geomagnetic storm. The second difference is that an interplanetary shock in the solar wind causes a secondary compression of the magnetosphere. We measure the magnetopause within geostationary orbit again, and the last closed drift shell becomes compressed down to an L star of 4.3. There is a negative phase-space density at L star above 3.8, which means if there is high ULF wave activity, there will be indirect magnetopause shadowing occurring as electrons are diffused down the negative gradient and towards the last closed drift shell. If you would like to know more details about the work that I've shown, the paper is currently under review and is available online via the link. I will also be available for questions during the session on Friday. Thank you.